Okay. Hello, everyone. So, right now we know resistors, sources, current sources, voltage sources, and also capacitors and inductors. And if you remember, the major difference between capacitors and inductors and other elements like resistors is that they have the ability to store energy, either in the form of magnetic energy or electrical energy. Now, today's topic is transient analysis, and in order to understand what is it about, I'm going to start analyzing an example step by step and see what happens inside this circuit. So, in the circuit, the switch has been at position A for a long time. This is something that we are going to understand the importance of. But right now, just leave it. Now, this is the circuit, and the first thing I want you to understand is how the switch works. So the switch goes from A to B at t equals 0 based on the circuit. Do you see that? There's an arrow going from A to B, which means at t equals 0, the connection goes from A to B. Now, what does it mean? It means that, for example, at t equals -2 seconds, the switch is connected to port A, or to node A, or to point A, right? And at t equals, for example, 5 seconds, which is a positive time, it's connected to B. Making sense? Okay. Now, the first question is, what is happening in the circuit before we switch from A to B? Okay. So let me see. I'm going to copy the circuit here. And do you agree that before t equals 0, before switching, I can get rid of this part of the circuit? Do you agree that this is the circuit that I'm interested in? The left part of the circuit is completely irrelevant. Okay, now, what can I say about the inductor in this circuit? Why? Say it louder. Red. Was that you? Okay. Is it a wire? Why?
You have no change in voltage anymore, it's just like not storing anything. It's kind of a headache stuff, I guess.
That's correct. I mean, there's nothing wrong. But do you see the connection between what he said? He said it's fully charged, and the sentence, the switch has been at position A for a long time. It means that whatever was supposed to happen to the inductor, it has had enough time for everything to settle down and go to a steady state. Okay? That's why we say either the inductor is fully charged, everything is in a steady state, or if you remember the previous lecture, I mean the lecture before the last one about inductors, how does inductor behave in DC circuits? It behaves as a short circuit. Is this a DC circuit or no? Yes. IS is constant. Do you see that? The term IS is constant. It's not changing by time. So this is a DC circuit. So what can I do to IL? Just replace it with a piece of wire like a short circuit. I'm going to do something else on the circuit. Instead of writing ILT, this is what I'm going to write. IL 0 negative. And can someone tell me or explain it to me why? What does it mean? I already explained it when I was talking about the in-class assignment, previous lecture. What does 0 negative mean? Right before the switching happens, right? So right before the switching happens, the inductor is like a short circuit because everything in the circuit is steady, DC, so there isn't any change in the current. That's why the voltage across the inductor should be 0, which means short circuit and everything else. Now, what can I do? What can I do else here? Is there anything that I can simplify in this circuit? I can get rid of the resistor R, right? It's being shorted out because there's a short circuit around it. Okay? So first let's read what is written here and then we will continue. So since Is is constant and the circuit has stayed in this condition for a long time, based on inductor equation, the inductor is in fact acting as short circuit. Okay? Now, I talked about the state of the circuit right before switching, and can you tell me what is the current passing through the inductor at 0 negative? It should be obvious, right? There's no current passing through the resistor, so all the current will go through the inductor. Any problem so far? This is a step 1 of our analysis. We analyze the circuit at right before switching, which is called t equals 0 negative or 0 minus. What happens when we switch from A to B? Let's copy the circuit again. So I should change the switch from A to B, like that. Any problem so far? Before asking my next question, let's see the statement of the problem, the example. What is it asking you to do? Find IL. Find the current passing through the inductor at all times, negative, positive, whatever. So is it fair to say that, again, the left part of the circuit, where it includes a current source and a wire, actually has nothing to do with the part that I'm interested in? Do you agree with that? Do you see the current source is connected to some circuit? It's just a wire, no problem. I'm not saying it doesn't exist, but is it affecting the inductor or no? No, because you see, it's not connected to point A, so it's completely detached. So I can do this. This is my circuit for positive time. Any problem with that so far? See, the left part of the circuit, it is still there, okay? But it's not connected to my inductor. So if I'm interested in finding IL, it's not going to affect that. It's not going to be affected by IS. Yes? Are you talking about the current source?
Yes.
The current source is connected to a wire, so the current will just go around. But it's not going to go to the right part of the circuit where I'm interested in finding the current for.
Oh, and you still have current though because it's inductor stores charge.
Oh, yeah. That was the next thing that I wanted to talk about. Yes. What I've covered so far is that I'm allowed to disconnect my current source from the part of the circuit that I'm interested in because they are not connected. Okay? Because the switch has changed from A to B. Now, okay, so if you are okay with this, I'm going to draw another circuit, but this time not generally for any positive t, but only for t equals 0 positive or 0 plus, which is right after switching. Before talking about this, I'm going to ask you a question. Focus on this circuit, just L and R, a piece of inductor connected to a piece of resistor on the table without being connected to any sort of source. Is there anything in this circuit worth calculating? Is there going to be any current or voltage in this circuit?
That one independently, man.
Sorry?
That one by itself.
Yeah, that one by itself, just that L and R. Pay attention. Is there anything in this circuit that is non-zero? Current, voltage, whatever.
Yes.
What is it? Okay, so the inductor, this is something that you all agreed on, right? You all agreed that the inductor was fully charged before switching, right? Someone said it. I think it was red. So it was fully charged. After you disconnect the left part of the circuit, what happens to the current of the inductor? Can it drop 0 instantly? That violates that boxed statement. The current of the inductor cannot change abruptly. Okay? So what can you say? At t equals 0 positive, what's the current passing through the inductor? IS. It cannot change. It should stay the same. So if I want to simplify my circuit, what should I replace the inductor with for t equals 0 positive? Current source. Right? And what is the value of this current source? It's IL0 positive, which is equal to IL0 negative, which is equal to IS. So before t equals 0, the inductor was connected to an independent source, and it stored energy. Now that the inductor is disconnected from the source and connected to just a resistor, it will release its energy to the resistor. Okay? We already answered this. Next question, which is IL0 positive is equal to IL0 negative. And again, what's the reason that we are allowed to write this? Yeah, inductor current cannot change abruptly. My next question. I said at t equals 0 positive, this is your circuit. Is the circuit the same at t equals 1 second? Why not? It will lose some of the energy. So the value of that current source air coat is going to be smaller and smaller until ultimately it becomes 0, right? It will lose all of the energy over the resistor. Any problem with understanding the second step? So the first step was t equals 0 minus. The second step, t equals 0 plus. And now we talked about 0 positive, but we didn't talk about, for example, t equals 5 seconds or 2 seconds or 10 seconds. What's going on in the circuit at that time? So the circuit looks like this. Right? This is your circuit. And we need to analyze this. What can we do for analyzing this? And just write a KVL. R ILT plus, what's the voltage across the inductor? L DIL over dt equal to 0. Just rearrange the equation. It's going to be DIL over dt plus R over L times ILT is equal to 0. What is this called? Have you ever seen that before?
Ordinary equation.
First order ordinary differential equation. Do you know how to solve it? No. Let's just stick with no. Huh? It's easier. Sorry? Dozens of methods. I preferred guessing. Okay, and here is my argument. So what is DIL over dt means?
The derivative.
The derivative. Okay, the first derivative. Okay, the first derivative plus some coefficient that I'm going to, let's rewrite it like that. Okay. I just defined L over R. I just called it a new name. Okay? I'm just calling it tau. Now, this is your equation. Let me explain it. The first derivative of a function that we don't know plus some coefficient of the original function is equal to 0. So it means that if you take the derivative of the function, it only adds a coefficient to it. The appearance, the general look of the function shouldn't change. What function has this property? If you take the derivative of it, it only adds some coefficient to it, but the main module, or the main unit of the function stays there. Exponential. Okay? That's called guessing the answers to a differential equation. Because of the way the differential equation is, I can say that the answer to this is an exponential function. So how should I write the answer? ILT is equal to, I definitely have some exponential, and I just guess, for some reason unknown, that the exponential is in this form, e to the negative t over tau. Like, you may ask why, okay? And I say for some non-obvious reason, if you plug that into the equation, it works, and that is enough for me. but it needs something else. K. If you remember, whenever you solve a differential equation, it always has a unknown constant. And if you have taken 245, Math 245 differential equation, you know that that constant should be determined using initial conditions or initial values. Okay. So let's determine K. Initial value. Okay. So ILT, if I plug 0 positive to it, why did I choose 0 positive, not 0 negative?
Because this applies.
Say it again.
This equation applies to 0 positive.
This part of the circuit that I'm analyzing, do you see that? It's for positive time, so I'm considering 0 positive. One might ask, what's the difference?
0 negative, it's IS. We already determined.
Well, 0 positive is also IS, right? So they are equal.
But that's the initial value. That's at that moment.
Yes, so let me put it this way. For this specific circuit, it doesn't matter which one you choose. Because the fact that it's an inductor, the current cannot change abruptly and both of them have equal values. But what if it was a resistor? Then it could jump, okay? So remember that this is IL 0 positive. Okay, what is the value of IL 0 positive from the previous part? IS, right? And what is the value of IL 0 positive from the equation that I found? So what does it mean? That K is equal to IS. So the updated equation is this. ILT is equal to for negative time, it's equal to IS. For positive time, what is the value? Let me write it like that. IL0 negative is equal to IS, and here is IL0 positive e to the power of negative t over tau, and that is equal to IS e to the power of negative t over tau. They are the same. This only applies to, no, it's for every time. And what is tau in this specific circuit? L over R. Okay, I'm done with the example. I found the current IL for all time, for negative time and for positive time. Now let's plot this guy. So what is the value of the current at 0? IS. This is IL0 positive equals to IL0 negative, and it's equal to IS. This. What happens after?
Curves downward.
exponentially goes die, right? Decays. When does it reach zero mathematically? It doesn't. So t equals infinity, it will die, right? It's immortal. The function here is IL0 positive times e to the power of negative t over tau, and tau is L over R. What do we call this portion of the plot? We call it a steady state. Right? Because everything was a steady. Because it was in that situation for a long time. What do we call this guy? Or this part? Transient response. And what do we call this part? Again, steady state. We don't mathematically reach that, never, but the fact that I'm saying mathematically is because physically the situation is different. I mean, for a circuit, 10 seconds might be enough, so you don't actually, so you're not able to count or to measure anything after 10 seconds because the current is so small that no measuring device can actually measure it. So we consider it as zero. Do you see the difference between the mathematically and physically? And that's what I mean. Okay, any problem? Good. Now, we did everything for ILT. Now let's find the voltage across the resistor. The voltage across the resistor. So this is what I'm going to do. I'm going to first analyze the circuit at t equals 0 negative. So at t equals 0 negative, the circuit is like that. If you remember, the inductor was replaced with what? Short circuit. And also I'm going to change the labels, IL0 negative and VR0 negative. Can someone tell me what is VR0 negative? It's 0. Why? Because the resistor R is shorted out. What does it mean? What does it mean when something is shorted?
There is no resistance.
No, the resistance is still there. What doesn't pass through it? There's no current passing through that. So based on Ohm's law, the voltage across it should be 0. Okay? Any problem? See, it's shorted out. So the voltage across it actually, or easier, you don't have to use Ohm's law. I mean, exactly. The two nodes are connected with a wire, so the voltage difference is 0. Okay. So let's now analyze the circuit at t equals 0 positive. Okay, this is your circuit. I'm going to change the labels to VR0 positive, and I don't need this. I don't know why it's there. And I need to change this one also. IL0 positive. What should I do to the inductor? Replace it with current source. 0 positive, right? And the value of the inductor is IL0 positive equal to IL0 negative, and it's equal to IS. So can someone tell me what is VR0 positive? Negative IS. Did I use the correct direction? Yeah, negative IS times R. Right? Okay. What happens in the circuit at T equals, or T positive?
Instead of IS, it would just be the equation factor.
So let's bring the inductor back. You have ILT, and here you have VRT, right? For all positive time. Can you tell me what is VRT now? Should I solve the differential equation again or no? No, I already solved it and found ILT, right? Do you remember that? Green equation. So if I have ILT, what is VRT? Minus R ILT, right? Now substitute ILT from the previous equation, which is negative R IS e to the power of negative t over tau. Remember that that is for positive time, and tau is equal to L over R. Okay so far? Instead of writing negative RIS, what can I write? Look one line above. I can write VR0 positive, right? So let me write this and you tell me if everything is making sense. For negative time, the value was 0. For positive time, it's equal to VR0 positive e to the power of negative t over tau. Instead of writing 0 here, I can actually write it as that. VR0 negative, which is 0. Do you see what I did? I just, instead of this guy here, from the line above, I can write VR0 positive. And I use that to write my equation. Any question? Any problem? Remember that tau is equal to L over R. Now I'm going to copy this guy. Here. And I'm asking you to compare it with the red one. What do you see? What is your observation?
They behave the same.
They behave the same. Meaning that what is exactly the same in these two variables? Tau, the time constant is the same. The shape of the exponential is the same. The only thing that is different is the value at 0 negative and the value at 0 positive. Okay? So is it correct to say that if I analyze this circuit and find the time constant, then I can apply the time constant to all the variables in the circuit? You will see that in the summary where I'm talking about this, but just right now I want you to understand what's going on. So you see every variable in the circuit, in the same circuit, is going to follow the same exponential behavior. Okay, let's repeat everything for capacitor. So this is my capacitor circuit. The switch has been closed for a long time. You understand what closed means. It means that it is connecting the left to the right. And at t equals 0, what happens to the switch? It pops open, right? So what's happening in the circuit before we open the switch? Why?
Well, like, the wire passing over between the smart and the same. Yeah, well. Oh, actually, it isn't.
Okay, what do you replace a capacitor with? Open circuit, not short circuit, right? So what should I label this voltage? VC 0 negative, right? Okay. As you said it, Vs is constant. The circuit has stayed in this condition for a long time. Based on the capacitor equation and your knowledge of the previous lecture, your capacitor is acting as open circuit. No, I'm still in negative. That is for the next part. Yeah. So can you tell me what's the value of VC 0 negative? Is it obvious for everyone? They are in parallel, the voltage across. Okay. This is the first step. Let's go to the second step. What happens after switching? So this switch becomes open. Can I get rid of the left part of the circuit? Is it doing anything for the part that I'm interested in? No. So this is my circuit. This is for T positive. Now that we are here, can you tell me the equivalent circuit for T equals 0 positive? What should I replace the capacitor with? A voltage source. And what's the value of that voltage source? Why?
It stores charge just like the inductor, but instead
But yes, but why the value is Vs?
because it's been connected to start.
But that was for negative part.
Voltage can't.
Voltage across a capacitor cannot change abruptly, right? So VC 0 positive should be VC 0 negative should be Vs. And this is the part that I just said. VC0 positive is equal to VC0 negative, and it's equal to Vs. And the reason is because the voltage, or the capacitor voltage, cannot change abruptly. Okay? What's the next step? Then we analyze the circuit, write the differential equation, and solve it for R and C. Everything is the same. The shape of the exponential and everything is the same, except your time constant, instead of being L over R, becomes RC. And finally, even your equation. Let me actually change this equation to write the full length of it. That is for negative time, and that is for positive time. The only difference compared to the RL circuit is that your time constant is RC instead of L over R. Okay? You see the shape, the plot, everything is the same. The only difference is that your time constant becomes RC instead of L over R. Okay? And if you remember what we did in the first case after we found the inductor current, we continued the method and we found the voltage across the resistor, and we found out that they follow the same shape and function. I have done the same here. I found the current that's passing through the resistor, and if you look at that, again, you see that? It's the same shape. It's the same function. Now this is the summary. In a first order circuit, what do I mean by a first order circuit? If I want to get out of defining that for you, I can say a first order circuit is a circuit that gives you a first order differential equation. Okay? But a first order circuit is generally a circuit where this definition is not perfectly correct, but works for this course. If you only have one inductor or one capacitor in your circuit, that's a first order circuit. Okay? Let me ask you a question. Does it mean that if I have two inductors in my circuit, it's a second order circuit?
No.
Explain. They could be in parallel. You can combine them and still you have one. If there are in places in the circuit that you cannot combine them, then it will probably create a second order differential equation. Do we have to worry about them? Absolutely not. That's not the focus of this course, especially for chemical engineering students, okay? Electrical engineering students, I don't know how many we have. Yeah, a couple of, yeah, you need to worry about that later. But right now, we have only first order. Okay, any question? Okay, so in a first order circuit, where at t equals 0, the moment where, the instant where switching happens, if all the independent sources are disconnected from the energy storing element. So first of all the independent sources are disconnected at t equals 0. Isn't that the case that we covered today? At t equals 0, the independent source was disconnected from, what do I mean by energy storing element?
Inductors and capacitors.
L or C. Okay, now if you remember what happened, before disconnection, it has stored energy, and after being disconnected, it started releasing the energy until it completely is dead. Okay, so is it fair to say that the response of the circuit, the response means the variable that you're interested in? Every voltage or current, whatever you're after in the circuit, the response of the circuit is not due to some external sources, is it? Let me go back here to this equation. Look at the response of the circuit for positive time. Is it due to some current source or voltage source? No, because they are already disconnected. Then what is it due to then? The inductor and capacitor initial values, right? Or the stored energy. So that is because of the initial conditions at L and C, and hence it is called natural response. It's not due to external forces. You will see next lecture that we call the other case forced response. This is natural response, meaning that it's because of the initial condition of the inductor and capacitor. This is something that you need to memorize. This is the summary of this lecture, and I'm going to talk about that. There are a couple of things that are probably confusing you, and we are going to address them. Pardon me? Yes, except one thing is different, the time constant. Did I get your question right? Did you ask whether this equation applies to inductors and capacitors? Yes, it does, but with one difference. If your circuit is made of inductors and resistors, the time constant is L over R. If it is made of resistors and capacitors, then it is RC. Okay, so that part is different. So, two questions. First, what do I mean by why?
Current source or voltage.
Anything you're after. It can be a voltage of a resistor, voltage of an inductor, voltage of a capacitor. It can be the current of an inductor, the current of a capacitor, or the current of a resistor. So anything that you're after, I'm going to show it with why. Okay? So that's the first thing. Anything that you're after. Does this look like what we had found before? No, it doesn't. Why are you nodding? It does not. This is what we found. Isn't it? This is what we worked and found, right? The black one. So what is different in the red one? There's something that we didn't talk about. Y infinity. What does it mean? It means that the variable that you're after at t equals infinity. Okay? Let's see why I just added this without any explanation. Let's go back to our circuit. One of them. Let's go to the inductor one that we actually talked in more details. Okay, I think this part is good. Yeah. Okay, what happens to the current or voltage or whatever variable that you're after? What happens to them at t equals positive infinity? They are all zero. Can you tell me why?
Discharging until it hits zero.
It will be discharged until everything is gone. Is there any way that something is pushed into the circuit? Okay, if there was some voltage source or some current source connected to the circuit at t equals infinity, yes, it will be possible. But in this case, is it? No, that's why we call it natural response, right? Because everything is not because of any external sources, okay? So the fact that I've added this into my generic equation, first of all, confirm for me that for today's lecture, the black one is equivalent to the red one. Do you confirm? Because it's zero, y infinity is zero. So I've just added that too. Then why? Am I sick or something?
You can use it to find like a time, like if you're given, I want it to where my current equals this value, you have your initial, you have what your second current could be, and you can just solve for time.
But it is zero.
Well, not if you have like, well, if your time doesn't, that's only at t infinity.
No? What do you mean? Yeah, y infinity is zero. If I remove that from equation, I can still find the function at t equals 5 seconds. Right?
Yes.
Yeah. So it's not changing the equation. The reason is next lecture. The next lecture, we will learn about circuits that still have some sources connected to the L or C at t equals infinity, and that y infinity is not zero anymore. Okay? So why am I including them here? Because you only have to memorize one set of equations. Okay? The most generic form, the most general form. Now, it's very easy to just set y infinity equal to zero if it is natural response. Did that make sense to everyone? Okay? Yes?
So I assume basically to discuss this next lecture, but I was just curious, how do you have like it not go to zero, but it also work as a conductor does? Because it only acts as a conductor slash capacitor once it's disconnected, right?
It can charge and discharge. It doesn't discharge until it is dead. So, let me, can you repeat your question?
I was just asking, because I was thinking like to make y infinity not zero, you have some constant source, right?
Yes, there is sources still connected to the circuit.
But then if you do have that, then the inductor just acts as, or inductor acts as a short circuit.
It does, yeah, it does.
So how do you have this form happen with circuit or like a source? Like in that case, for example,
Let's just focus on this, okay? I'm not going to talk about this in details just to satisfy your urge. Look at this, Chaz. I changed the circuit a little bit. What's going on in the circuit before zero? Nothing. The inductor and resistor are just alone. They have been in that situation for a long time, so there is nothing in the circuit. They are just on the table. What happens at t equals zero positive? The source gets connected. It starts charging the inductor. At t equals infinity, what happens? It reaches IS. The resistor is completely bypassed, and all the current is passing through the inductor. Is it zero at t equals infinity? Not anymore. Okay? But this is something that we talk about next lecture. Now that I'm thinking about that, we don't need one whole lecture for that. I just covered it in 30 seconds. That is the whole discussion of the next lecture. Well, Monday I'm going to do your in-class assignments for you. So, but Wednesday we don't have a class. because I have to go to a doctor's appointment. But fortunately, that class is usually just wasting your time. You just come here, do a mini lab, and do your in-class assignment, which I have to do it for you now that I'm absent, and then you go home. So there's no class on Wednesday, okay? I will send you an announcement anyway. Okay, no question? Very good. Let's do another example, but this one, not the simple one that we had, like something that could actually haunt you tonight, huh? When you're asleep. Okay. We're going to do it step by step. The first step, we should analyze the circuit at t equals 0, negative. That's always the first step. Copy the circuit, put it here, and let's see what happens at t equals 0, negative. So the switch is at t equals, the switch is at A. What can I get rid of in this circuit? The 7 ohm resistor. What else should I do to this circuit? Okay, see, think of it this way. Which element you hate the most? No, current sources are very good. The inductor, right? That's the one giving you a headache. So focus on that one. Can you replace it with something?
The currents.
Yes. Remember, for a long time, it's been in this position. So everything is in a steady state and DC form. So what can I do? I can replace this guy with a short circuit. Next thing, the last thing I'm going to do is I'm going to change the labels consistent with the time that I'm analyzing the circuit at. Was it IL 0 negative? And this one is VR 0 negative. Did I say it right? Yes, VR and IL. Yes. Okay.
You can get rid of the 10 ohm resistor.
Yes. The 10 ohm resistor also gets bypassed. It's shorted out. So you will end up with this circuit. I'm very tired and I'm begging you, please don't stay for your in-class assignment and run away.
So what if you stay up till 1-4 this time?
Huh?
What if you stay up till 1-4 this time?
I don't even have the energy to talk back to you. You know what hurts me the most is that I have to go to a lab to 5. Huh? Okay. Do you agree that this is your circuit? Now, this is where IL 0 negative is, and this is where VR 0 negative is. I just simplified the circuit. Now, am I done with first step? No. let's go to the generic equation. What should I calculate from the first step? Y0 negative. And can you tell me, for that specific example, what is Y? This guy and this guy. The two things that the question is asking you is considered Y. Okay? So first of all, I have to calculate IL0 negative. What's the value? Current division. If you're using anything else, no, I never said that. He said that, remember. But if you're using anything else, you're wasting time. Okay? Which means you're stupid.
It's proportional, inversely proportional.
5 amps multiplied by 2 divided by 2 plus 3 is equal to 2 amps. Now, what is the next Y? VR0 negative. How do you find it? It's 3 ohm times IL0 negative, right? Which is 6 volts. Ohm's law. Any problem so far? We're done with the step 1. Remember, I've said it many times. The average, the grade average of the second exam is usually much higher. Okay? Like for the first exam is around 55 something. For the second exam, for my section, previous quarter was 79. Okay? I think 80. The reason is that the concept might look more complex, but it is very straightforward. You usually get one circuit with 5 following questions. What is the value of blah at t equals 0 negative? What is the value at t equals 0 positive? What is the time constant? What is blah, blah, blah? Okay? So it is very straightforward. If it clicks, it means that you're probably gonna get a good grade on second exam. Okay? Let's go to second step, which is analyzing the circuit at t equals 0 positive. What should I do? 0 positive. It means that I'm going to be connected to point B. What should I get rid of in the circuit? The left side is completely disconnected from the inductor, which I'm interested in. What else?
The inductor is a current source.
Yes, at t equals 0 positive, you can replace an inductor by a current source. Or you can replace a capacitor by a voltage source. What is the value of that? Why?
Because it's equal to the IL0.
I didn't understand the word you said.
It's equals to IL0.
Why?
Because
Because the current of an inductor cannot change abruptly, right? So IL0 positive, it's equal to IL0 negative, and we have that value actually. What is it? 2 amps. I'm going to change the label of this to VR0 positive as well. What do I need to find? What do I need to find on a step 2 before moving to the next step? Yes, we need to find VR0 positive. Tell me what to do. Sorry? Current division and Ohm's law. So I have 3 ohms, and I need to find the current that's passing through the 3 ohm. The current passing through the 3 ohm is 2 amps multiplied by 10 divided by 10 plus 7 plus 3. And that is equal to, is it 3 volts? Yeah. Step 2 is done. Okay? Step 3, something trivial for this lecture, but we're going to do it anyway just as a practice. We're going to analyze the circuit at t equals infinity. I mean, before even analyzing, you should tell me what's the answer. 0. But it's a good practice to see. Sorry? Yes, exactly. Everything will completely go away. So just remember, for t equals infinity, first of all, t still infinity is considered positive, so your circuit is, the left part is completely disconnected. You have this. I'm going to change the labels as well, just as a practice, VR infinity. What happens to the inductor and why?
It's a different, it's a current source, but it's like a change.
It's a current source?
Well, at T infinity, it's the current source is no longer doing it.
What can I do with the inductor?
Just get rid of
At infinity, yeah.
Just get rid
Or
of
after infinity. I don't know what's the difference.
Just get rid of
Disappear.
What do you mean, open it?
Sure.
It was never there in the
Short it or open it? Why? That's how it behaves. What does an inductor behave under DC condition? Short circuit. Remember, you are only allowed to consider this under DC condition. Is there anything, any changes that you notice in the circuit? Nothing is changing at infinity because it has enough time, everything is settled, right? So you replace it by a piece of wire. So what is the value?
0.
Yeah, why?
Because there's nothing going on.
It's like you have connected a bunch of resistors, you put it on the table. They're not connected to anything. Done. This is the third step. Fourth step is to find the time constant, very important. Let's go to where our original circuit was, here. What was the time constant for this circuit? L over R, right? But the circuit was very easy. It was L connected in parallel, or in series or parallel doesn't mean anything here because you only have 2 elements. So from the terminals of the L, you have 1R, and you say the time constant is L over R. What if instead of 1R, you have a whole network? Find the equivalent resistance from which terminals? The terminals of the inductor. Did that make sense to everyone? Right? Compare it with this guy, see? From the terminals of the inductor, whatever resistor, whatever equivalent resistor that is connected to the inductor is going to act as your equivalent resistance used in the formula for time constant. So basically, these two circuits are summarizing what I was talking about. So look at LEQ and CEQ terminals and then find whatever equivalent resistance is connected to the rest of the network. Okay, so let's bring down the circuit one more time. Let's get rid of the extra parts because remember, I'm only considering the circuit at t equals t positive, right? Because that's the only time that the circuit has a meaningful time constant. I'm going to get rid of all the labels because I'm not trying to calculate any voltage or current. What else? I'm going to remove that and do this and find the equivalent resistance from these two terminals, right? And this is something that you've done before. What is REQ? 7 ohms plus 3 ohms in parallel with 10 ohm, which is 5 ohms. And then what is tau? LEQ over REQ. What is LEQ? 150 millihenry divided by 5 ohm, which is 30 millisecond, which is equal to 0.03 second. Sometimes I may find 1 over t as well because that makes my next step calculation a little easier. 100 over 3, which is 33.3 second inverse. What is the step 5? You have calculated everything required to plug into the generic equation and find your y's. Okay? So how many y do I need to consider for this example? 2. First one is ILT. What are the values? What is IL0 negative? 2 amps, right? What is IL0 positive? 2 amps. What is IL infinity? 0. So inside the brackets, 2 minus 0, 2, e to the power of negative 1 over tau times t. What is 1 over tau? 33.3 t. Plus y infinity, which is 0 amps. That is for t negative, and that is t positive. I shouldn't, yeah. What is the other variable that I'm interested in? VRT. What is the voltage VRT at t equals 0 negative? 6 volts. What is 0 positive? I don't know. What was it? 3 volts. What is infinity? So 3e to the power of negative 33.3t volts. That is for t negative, and that is for t positive. Question. If this circuit is given to you, okay? And they ask only one question from you on web work, one question. This is usually not the case on exam. On exam, you get one circuit and probably 4 or 5 questions. But in web work, if you get the same circuit and they ask you just this, find the voltage across the resistor at t equals 3 seconds. What should you do? You do everything exactly like this. You should start from a step 1 and do everything step by step and get to this. And one extra step is plug in 3 to t. That's it. One more thing. Is the current of the inductor changing abruptly at t equals 0? No. Is the voltage of the resistor changing abruptly at t equals 0? Yes. Is that a problem? No. Do you have any problem? What? You're hungry? Yeah, me too. Okay, let's do another example and then get the hell out. Andrew, start the process. Analyze the circuit at t equals 0 positive, 0 negative. First step. Tell me what to do to the circuit. No. Oh, sorry. E10. I said. Okay, Andrew, say. Let's start from there. Yeah.
I'll start by trying to combine most of the goods. I don't remember what it was, I don't remember how to start it, but that's how I start with, start buying stuff. And figure out
Are you joking? Preston. Okay, first tell me what to get rid of, what to simplify, what to change in the circuit at t equals 0 negative. The first thing is that I'm going to remove the sign for switch because the switch should be connected. What else? Yes.
Set the capacitor to a voltage.
Yes. Why?
Because it has been connected the entire time.
Yes. It's been in that position for a long time. What else? Change the labels. So this is VC0 negative, and this is VR0 negative. What do I need to find for first step to be done? They are screaming in red. VR0 negative and VC0 negative, aka Y, right? Y in that generic equation. Why? Because the question is asking you to. Right? Isn't that enough? How do I find VC0 negative and VR0 negative? Let's go with Braylon. Nodal, perfect. I mean, I usually say that any method that you use is not going to change a lot the time that you spend, but for this specific one, is it too obvious that nodal is better?
I think everything is, we have like at least 5 variables.
Sorry? Oh. Is it obvious why nodal is better? You're looking for what? 2 voltages. You can do them at the same time. If you go for Mesh analysis, you find the currents, then you have to write another extra equations to find the voltages, right? Okay. What do you call the red node? What do you label it? 10 volts. What do you label the purple one? VR. I'm going to drop the zero negative just for my system of equation. How do you label the green one? Nodal analysis, KCL at VR. VR minus 10 over 4 plus VR minus 0 over 6 plus VR minus 0 over 5 plus VR minus VC over 3 is equal to 0. KCL at VC. VC minus VR over 3 plus VC minus 0 over 12 is equal to 0. Two equations, two unknowns. VC 0 negative is equal to 2.93 volts and VR 0 negative is equal to 3.66 volts. Good? Okay. Let's go to step 2. Look. You want to do it? Step 2. First of all, I'm going to help you. The switch gets opened, so I remove the left part of the circuit completely. Now, this is your circuit. Tell me what to do to this circuit to make it prepare for t equals 0 positive.
Replace the capacitor
With voltage source. What is the value of voltage source? I don't know, 2.93. So that is VC 0 positive equal to VC 0 negative and equal to 2.93 volts. And I'm going to change this label to VR 0 positive. Right? Okay. What do you need to find? VR 0 positive. Look, can you tell me what is the value of VR 0 positive? You're getting close. First you said 2.93, then you said, oh no.
I thought it was parallel.
What that caused, oh no? Which element caused that, oh no?
The resistance,
Which one?
3 ohm.
Okay. So the 2.93 is across two resistors, 3 ohms and 5 ohms. So what do you find, what do you do if you want to find the voltage only across the 5 ohm? Voltage division, right? 2.93 volts times 5 ohm divided by 5 ohm plus 3 ohm, and the value is 1.83. Step 3. Jonah, you ready or no? Alina, you say you're not ready? Okay, let's go with Samuel. Tell me what to do at infinity. Before telling me, I mean, we're doing this just, I mean, we have extra time apparently. What is the answer? What answer do you expect to get from the third step analysis? For today's lecture.
I really don't get one answer.
0, because there's nothing going to exist in the circuit. What can how do you make this circuit infinity friendly? Capacitor, replace it with what? Open source. And change the labels as well. Now, what are the values? What is VC infinity in this circuit? Why? There isn't anything in the circuit. Do you see anything? A bunch of resistors connected together on a table. Nothing. What is next step? Find the time constant. Sorry? I mean, I don't care how you do it. You can combine all of them. And don't think this is something from the text, but this is just how I did it myself. Okay, what should I do? First of all, remove all the labels because we don't, not the values, the variables. Then, remove the capacitor. Don't replace it with anything. Create 2 terminals from across the capacitor to find the equivalent resistance. So, what is Req? Let me do this. I want you to understand that this circuit is actually like this. I want you to see that this is the same. And then you can see that Req is equal to 5 ohms plus 3 ohms in parallel with 12 ohm, which is 4.8 ohms. I need more space. Okay, so what is tau? REQ CQ, and it's equal to 4.8 ohms multiplied by, what was C? 60 millifarad, and it's equal to 288 millisecond. Can you also tell me what is 1 over tau? Just divide 1 by 0.288. 3.47, that's enough. Second inverse. Sorry?
No, never mind,
Yeah. Plug in. How many Y's? 2. What is the first one? VCT. Tell me the values. What is VCT 0 negative? VC 0 negative? 2.93. Yeah. What is positive? 0 positive? 2.93. What is infinity? 0. So 2.93 e to the power of negative 3.47 t volts. That is for t negative. That is for t positive. And then VRT. I'm very happy because the class is being done. Thank you. Thank you for all the energy. 1.83 e to the power of negative 3.47 t. What should we say now? Have a good weekend. Sorry?